Welcome to Everyday Mathematics. Today we look at Bernoulli's integral, which is the integral from x equals to 0 to x equals to 1 of x to the power x. So this is a complex integral, and by complex I mean complicated. And this was solved by John Bernoulli in 1697 for the very first time. This is in the book Inside Interesting Integrals, for those of you who may be interested in diving deeper. So without much ado, I'd like to now move forward to the solution bit of this problem. Before I even move there, I'd like to encourage those of us who are visiting here for the first or second time, if you haven't subscribed, please do consider subscribing to our channel. Your support would go a long way in giving us that extra visibility that we do need. And if you like what you see, please don't hesitate to leave a like. If you know somebody might be interested in what we're doing here, please do share with them this video. So let's move on to the solution bit of this problem. So our problem is the definite integral from x equals to 0 to x equals to 1 of x to the x. Okay, so the first thing we're going to introduce is we're going to come up with a function y, which is equal to x to the power c times x to the power a. And since we know, I'd like to just do a side analysis here, since we know that x is equal to e to the power natural logarithm of x, then we can say that x to the power c, x to the power a is equals to e to the power natural logarithm of, in bracket, x to the power c x to the power a, which is equal to, using the rules of logarithm, e to the power c x to the a natural logarithm of x. Okay, so this is important for us, and I'd like to just enclose that in that square. Okay, now let's also remind ourselves about one more thing. We know that e to the y is the same as 1 plus y plus y squared over 2 factorial plus y cubed over 3 factorial, and so on and so on and so on. So we'd like to keep that also in its own rectangle as shown there. So what does that mean for us? It means for us that now e to the power c x a times natural logarithm of x would be equal to 1 plus cx to the power a natural logarithm of x plus 1 over 2 factorial c squared x to the power 2a log of x squared plus 1 over 3 factorial c cubed so on and so on and so on. So this is our third expression. So let's move forward. Since this guy is our integrand, and there is a link here, and what we have here, and obviously there's a connection here and this connection here, it means our integral now becomes 0, 1 of e c x a natural logarithm of x, which is equals to okay, let's see, c squared over 2 factorial 0 1 x 2a plus c cubed over 3 factorial 0 1 x 3a right? So that is what our problem has become. And so previously we saw that our problem had become this interesting series. And this is, let's pull C out, 0 1 x a of x plus c squared over 2 factorial 0 1 x2a log and so on and so on. So what we see a pattern here. So we, for example, we see 2a and then 2. So let's get a general integral just to help us solve this problem. And I'm going to use some form of color coding here. So if we have an integral from 0 to 1 of x to the m log to the n of x, this can also be expressed as from 0 to 1 the derivative of x to the power m plus 1 over m plus 1 log n x. And so if we're using integration by part, what does integration by part tell us? That if you have a product of function v and the derivative of function of u, if you integrate that, you have uv minus u, the derivative of v, right? So if we have that, then it means that we do now have 1 over m x to the power m plus n log of n x 0 to 1 minus from 0 to 1 1 over m plus 1 x to the power m plus 1 and then the derivative of log to the n x, okay, which is equal to limit as x tends to 1 of 1 over m plus 1 here, rather, I'd forgotten it. So this is that, and then x to the power m plus 1 log n x minus limit as x tends to 0, 1 over m plus 1 x m plus 1 log n x, and then minus 0 to 1, we have 1 over m plus 1 times n log to the n minus 1 x times 1 over x dx. Okay, so this, as we see, this goes to 0 because log of 1 is 0. This goes to 0 because 0 to the power n plus 1 is equal to 0. And so we are left with negative m plus 1, 0 to 1. We add x to the power m plus 1, and we had n here. We had log n minus 1 x, and then we have 1 over x. So this becomes negative 1 over m, 0, 1. This guy here and this guy interact, so we have x to the m, 1 over m. And then we can even bring this n out so that we now have n there. That. So, and we can continue by saying we have n over n plus 1, 0, 1. Again, we repeat the process. X to the power m plus 1, m plus 1. Okay. And then we use integration by parts, where now we have, right? We have 1 over m plus 1 x m plus 1 log n minus 1 x 0, 1 minus integral 0 to 1 over m plus 1 x m plus 1 times the derivative of log to the n minus 1 x. You see that this would go to 0 in its entirety, so that now we do have m plus 1 minus 1 over m plus 1, 0 to 1, and then we have x m plus 1, we have n minus 1 log n minus 2 with x, 1 over x. This and that would interact. So now we have negative n plus 1, and then we can pull this out. So we have negative n minus 1 over m plus 1 integral of x to the power m log n2 x. And we see that this continues until we have all the way until we have negative 1 over m plus 1, 0 to 1, x to the power m, and log to the power 0 would be 1. So we have that, and this becomes negative n, m plus 1, negative n minus 1 over m plus 1, all the way to negative 1 over m plus 1. Here we have 1 over m plus 1, x m plus 1, 0 to 1. And so this goes to 1. So essentially what we have is we have negative n over m plus 1, negative n minus 1 over m plus 1 all the way up to negative 1 over m plus 1, and then we have 1 over m plus 1. And so we can see that we have negative 1 to the power n, and we have n factorial, and we have m plus 1 to the power n plus 1. Therefore, if you had an integral from 0 to 1 of x to the power m times the natural logarithm to the power n of x, that is equals to negative n over m plus 1 n plus 1. So this was just a by the way, and so we are going to continue. And what was our problem? And by the way, before we even embark on the problem, we're going to write what we've found, that an integral from 0 to 1 of x to the power n log to the power x is equals to negative 1 to the power n factorial over m plus 1 to the power n plus 1. So this would be in a square somewhere, right? Such that having known that our problem from 0 to 1 of x to the x, x to the c x to the power a dx being equal to 0 to 1 of e to the power c x a log of x, this being equal to 0 to 1 dx plus c 0 to 1 x to the a log to the 1 of x plus c squared over 2 1 0 to 1 2 factorial rather x to the power 2a log square of x c cube over 3 factorial 0 to 1 x to the power 3a log and so on. It means that if we look at this power, consider this to be m, this to be m, this to be m, and this to be n, whatever is, there's a 1 here, this to be n, this to be n. It means we have, since we have 1, this will be 1 plus c, then we put negative 1 to the power, since this n is 1, 1, and then 1 factorial over m is a plus 1 to the power n is 1 plus 1 is 2. Okay, plus c squared over 2 factorial times this here, we have negative 1 squared 2 factorial over n is 2a, m is 2a plus 1 to the power n is 2 plus 1 is 3 plus c cube over 3 factorial negative 1 to the power 3 factorial over, we have 3a plus 1 to the power 4, and so on and so on and so on. So we see this is 1, there's a hidden 1 there, there's 2, this one cancels, this one cancels. So essentially what we do have is an interesting expression, because now we have eliminated the integrals, and now we do have a more simplified expression, because here now we have a negative here, this is a positive, and this is a negative. Okay. So what we see is our problem from 0 to 1, e to the power cxa log of x is equal to 1 minus c over a plus 1 squared plus c squared over 2a plus 1 cubed minus c cubed over 3a plus 1 to the power 4 plus c to the power 4 over 4a plus 1 to the power 5, and so on and so on and so on. So since this problem is also the same as 0 to 1 of x to the power c x to the a, it means when a is equals to c equals to 1, that's when we have the integral x to the x, right? Which is equals to 1 minus, here we have 1 over 2 squared, since this is 1, 1 plus 1 is 2, plus 1 over, this is 2 plus 1 is going to be 3, so 3 cubed, minus 1 over, this is 3, so we have 4 to the power 4, plus 1 over 5 to the 5, and so on and so on and so on. So this here is our answer, and so I'll just maybe draw a straight line there. It doesn't stop there. We can also look at other scenarios where obviously a is probably 1, and I mean let's look at, so we have integral from 0 to 1 of x to the power c x to the a being equal to 1 minus c over a plus 1 squared plus c squared over 2a plus 1 cube minus c cube over 3a plus 1 to the power 4 plus c to the power 4 over 4a plus 1 to the power 5, and so on and so on. So a couple of things, if c is equals to -1 and a is equals to 1, that means we have the integral 0 to 1 x to the power -x, which is equals to 1 plus 1 over 2 squared plus 1 over 3 to the power 3 plus 1 over 4 to the power 4 plus 1 over 5 to the power 5, and so on and so on. If, for example, we say, okay, if c is equals to 1 and a is equals to 2, that means our integral is 0 to 1 of x to the power x squared, which is equals to 1 minus 1 over, here we have 2 plus 1, which is 3 squared, plus 1 over 2 times 2 is 4 plus 1, so we have 5 to the 3 minus 1 over 3 times 2 is 6, so we have 7 to the 4 plus 1 over 4 times 2 is 8, so we have 9 to the 5, and something, and so on and so on. Okay, so we've seen that scenario. What if, obviously bearing in mind that we have still xcxa being equal to 1 minus c over a plus 1 squared plus c squared over 2a plus 1 cubic minus c cubed over 3a plus 1 to the 4 plus c to the power 4 over 4a plus 1 to the power 5. What if, for example, we say that c is equals to 1 and a rather is equals to a half. So in other words, 0 to 1, x to the power x to the half, which is also equal to 0 to 1, x to the power square root of x. This would be equal to, so a is a half, so we have 1. That remains the same, so we have 1 over 3 over 2 squared plus 1 over 2 cube, because here we have 2 times a half, which is 1, and then here we have 1 over 3 over 2 plus 1, which is 5 over 2 to the power 4, 1 over, so that is 2 plus 1, which is 3 to the power 5, so on and so on and so on. So let's probably stop there for now. But what we've seen is we can use that general expression to really derive a number of interesting integrals with a power that is in the form of x something, right? So you could even say a is a third, a is a quarter, so to get those roots also figured out. So that really brings us to the end of our video today. Without much ado, I'd like to really thank you for keeping it locked. If you haven't subscribed to our channel, we do encourage you to subscribe to our channel. If you like what you see, please leave a like. Until next time, bye bye.